నమస్కారం. డాక్టర్ బిఆర్ అంబేద్కర్ సార్వత్రిక విశ్వవిద్యాలయం విద్యార్థులకు స్వాగతం. ఈ ప్రసారంలో
Today we are going to learn a key theorem in the theory of Galois. Before we do it, we do some introduction to this theory. Till 16th century, there were many pending problems, unsolved problems. In classical algebra, polynomial equation is to be solved in a formula, but a quadratic equation has a formula, but other equations have no formulas to find. But in 16th century, Raphael and Italian mathematicians could find formulas for cubic equation and quartic equations. But for quintic equation, for 3 centuries, nothing could be found. In 19th century, Raphael and Abel could produce some quintics which could not be solved in radicals. Then a beautiful French mathematician could give us beautiful ideas through which we could dissolve all these unsolved problems of 16th century and 19th century, and it was in handy field theory and Galois theory. Galois theory associates very close relationship with the fx belonging to fx, a group called Galois group of fx over f. This group is a permutation group of roots of fx. It is introduced through the splitting field k of fx over f. So, before I take up the main theorem, I require some definitions and results which you have already learned. An irreducible polynomial over a field f is a polynomial which has no roots in f, and an automorphism of a field k is nothing but a mapping from k onto k, which is 1 1 and onto, and preserves both the additive and product structures. Fixed field of a group of automorphisms of a field. Fixed field of a group of automorphism field k means if G is a group of automorphism of k, and those elements of k which are fixed by every member of the group is called the fixed group of the automorphisms of k, and it is denoted by kh if h were the group. Next, GKF. F automorphisms of k form a group by itself, and it is called a Galois group provided it is finite and f is a fixed field of the GKF. A normal extension of a field k. An extension field k is called normal extension of f provided a degree of extension over f is finite and the fixed field of GKF is f itself. Splitting field k of a polynomial over a field a polynomial fx over a field f. It is a minimal extension field in which fx splits into linear factors. That is called a splitting field. Now we do require some of the results which you have already studied in the earlier chapters. So first theorem is, if f is of characteristic 0, if AB are algebraic over f, then FAB equal to FC for some C belonging to FAB. AB algebraic over f, B is algebraic over f, and FAB is the field extension obtained by adjoining A and B. Then we can find a primitive element C in FAB such that by just adjoining C to F itself, we could get a FAB. So, this result tells that whenever you have a finite extension, the extension field will be simple extension. And a second theorem is, if Px is belong to Fx and Fv is a root of Px, then Fv is isomorph to F dash W, where W is a root of P dash T belong to F dash T. It can be so chosen so that V sigma equal to W and alpha sigma is alpha dash for every alpha belong to F. That is the restriction of this isomorphism would be the isomorphism of the fields F and F dash, and this isomorphism maps V onto W. Any two splitting fields E and E dash of two polynomials Fx belong to Fx and F dash T belong to F dash T respectively are isomorphic by an isomorphism phi with the property that alpha phi equal to alpha dash for every alpha belonging to F. It is again the restriction of this isomorphism will be the isomorphism of the F and F dash. Theorem 4, and this we shall, from here onwards we will be giving you the proofs of the theorems also. If K is a field and if sigma 1, sigma 2, sigma n are distinct automorphisms of K, then it is impossible to find elements alpha 1, alpha 2, alpha n not all 0 in K, such that alpha 1 sigma 1 u plus alpha 2 sigma 2 u etc. alpha n sigma n u equal to 0 for all u belonging to K. So this is impossible. That's what the theorem says. Suppose it is possible to find not all alphas are zeros, such that I equal to 1 to n sigma alpha I sigma I u equal to 0, therefore all u belong to K. Then some of them are 0, so we will drop the 0 terms. Without loss of generality, assume that alpha 1, alpha 2, alpha m are all non-zero and alpha m plus 1, alpha m plus 2, alpha n are all zeros. Then alpha 1 sigma 1 u plus alpha 2 sigma 2 u etc. alpha m sigma m u for all u belong to K. Then this mark this as first equation, and this left hand side expression is the minimum expression with this property. That is what we assume. Now suppose if m equal to 1, then say alpha 1 sigma 1 u equal to 0, u for every u belong to K, put u equal to 1, then sigma 1 is 1, so alpha 1 into 1 is 1, so alpha 1 is 0, hence all alphas are 0, therefore the theorem is true. Suppose m is greater than 1, then these are all distinct automorphisms. Sigma 1 is not equal to sigma m would mean there exists at least one point C belong to K such that sigma 1 C is not equal to sigma m C. Alpha 1 sigma 1 C u, then C is the element of K and u is the element of K, Cu is also element of K. For all elements of K this expression is true, the equation is true. Therefore alpha 1 sigma 1 Cu all plus alpha 2 sigma 2 Cu etc. alpha m sigma m Cu equal to 0. Then applying the automorphism property alpha 1 sigma 1 C alpha sigma 1 u plus alpha 2 sigma 2 C sigma 2 u etc. alpha m sigma m C alpha m u is equal to 0. Then multiply first equation by sigma 1 C and subtract from 2, then you will get sigma alpha I sigma I C minus sigma 1 C sigma I u equal to 0 for all u belong to K. And this contradicts our assumption that the left hand side expression is the least one, whereas this the length of this third equation is smaller than the length of the first equation, which contradicts our assumption. Therefore our assumption that theorem is wrong and hence theorem is true. Now next result I require to do my goal is theorem 5. It is K is a finite extension of F, then GKF is a finite group and its order satisfies this inequality. 0 order of GKF is less than or equal to degree of K over F. If possible, suppose that GKF order of GKF is greater than degree of K over F, which is equal to m. Then consider m plus 1 automorphisms belong to this group. Sigma 1, sigma 2, sigma m plus 1 belong to GKF. Then sigma I equal to 1 to m plus 1 Ci sigma I Kj xi is equal to 0 for j equal to 1 to m, where k1, k2, km is the basis of k over f, and for all j equal to 1 to m, this is a system of m homogeneous equations in m plus 1 variables x1, x2, m plus 1, xm plus 1, and sigma I, kj are all in k. Therefore, it is this is a system of first one is a system of m homogeneous equations in m plus 1 variables xi's, I equal to 1 to m plus 1, kj, j equal to 1 to m. So, these are the m equations in m plus 1 variables, and therefore, it has a non-trivial solution, say y1, y2, ym plus 1. Therefore, sigma ci, sigma I, kj, yi is equal to 0, j equal to 1 to m. Now, let u belong to k, then u equal to sigma alpha j, kj, j equal to 1 to m, then which would imply that sigma ci, sigma I, alpha j, kj, yi equal to 0, which would imply that sigma ci, sigma I, sigma j equal to 1 alpha j, kj, yi equal to 0, which implies I equal to 1 to m plus 1 ci, sigma u, yi equal to 0 for every u belong to k, contradicting the theorem 4. Therefore, this has come because of our assumption that order of GKF is less than order degree of k over f. Therefore, order of GKF is not greater than degree of k over f. Therefore, order of GKF is less than degree of k over f. Now, sixth theorem, which is also required to do my main theorem. Let k be a normal extension and let H be a subgroup of GKF. So, once it is a normal extension, it should be a finite extension. Now, let kh be equal to x belong to k, sigma x equal to x for all sigma belong to h be the fixed field of h. That means, if all those elements of k which are fixed by every member of h will form a subfield of k. If x is fixed and y is fixed, x plus y is fixed, x minus y is fixed, x into y is fixed, therefore, it becomes a subfield of k, and it is denoted by kh. Then what we have to prove is degree of k over kh is order of h and h equal to gk kh. In particular, if h equal to gkf, then degree of k over f is equal to order of gkf. Proof: let h be a subgroup of gkf, kh be the fixed field of h. K is a normal extension of f would mean k is a finite extension. Once k is a finite extension, k is a finite extension of kh. K is a finite extension of f would mean k is a finite extension of kh, because f is contained in kh is contained, f is contained in kh is contained in k. Therefore, sigma belongs to h. Therefore, what would have order of kh, order of gk kh is less than or equal to degree of k over kh, because every member of gk kh, every member of h is a member of gk kh, and this of course by earlier the order of gk kh is less than k over k, because it is a normal extension. In the normal extension, order will be less than this. Now, sigma belongs to h means sigma belongs to gkk. Therefore, h is contained gkkh. Let sigma 1, sigma 2 be distinct elements of h. Then degree of k over kh is finite, which implies there exists a belonging to k such that k equal to kha, because every finite extension is a simple extension. That is what we have seen. Therefore, there must exist a primitive element a in k which generates k over kh. So, let px be equal to I equal to 1 to nh x minus sigma a. That means it is x minus sigma 1a into x minus sigma 2a into x minus sigma 3a up to x minus sigma ha. So, this product when you expand will be of this form: Px is equal to x power h minus alpha 1 x power h minus 1 plus etc. minus 1 power h alpha n alpha h, where alpha I are elementary symmetric functions. So what do we mean by them? So when you expand, what is the coefficient of x power h? 1 only. What is the coefficient of x power h minus 1? Is sigma 1a plus sigma 2a plus sigma 3a etc. sigma ha, that is alpha 1. So if you pick up any element from h, sigma from h, and operate on alpha 1, sigma alpha 1 will be sigma 1a, sigma 2a up to sigma na, and sigma 1a, sigma 2a, sigma na are nothing but same terms in different order, since sigma I is not equal to sigma j if I is not equal to j. Therefore, these are all distinct terms, and that means the same terms again repeat. Therefore, it is invariant. It is the sigma alpha 1 is alpha 1 only. Similarly, for every sigma belong to h, sigma alpha 2 is alpha 2, sigma alpha 3 is alpha 3 etc. sigma alpha is alpha I. Therefore, all these alphas are fixed by every member of h. Therefore, it belongs to fixed field, they belong to fixed field of h. The fixed field of h is kh. Therefore, they are all in kh. Therefore, this is a polynomial over kh. Now, sigma 1 is sigma 1a. Sigma 1 is identity automorphism. One of them must be identity. So, sigma 1 without loss we take sigma 1 as identity. Sigma 1a is a, so it is satisfied by a. But a minimal polynomial satisfied by a over kh is of degree m. Therefore, h must be greater than or equal to k over kh. So, by our earlier inequality, this inequality and this argument, what we conclude that h is equal to gk which would give the theorem is true. And in special case, when h is gkf itself, degree of k over f is equal to order of gkkh. Now, theorem 7, main theorem. What is that? A field k is a normal extension of a field f if and only if k is a splitting field of some polynomial over the field f. Assume that k is a normal extension of f, then k is a finite extension of f. Then there exists a belong to k such that k equal to fk. Consider the polynomial px is a pi I equal to 1 to n x minus sigma a, just like what we have done in earlier theorem, same way we are doing over k. Then where sigma I are elements of gkf, I is equal to 1 to n. Sigma 1 is identity automorphism. So, expanding px again you have x power n alpha 1, x power n minus 1 etc. minus 1 power n alpha n, where alpha 1, alpha 2, alpha n are elementary symmetric functions. So, what is alpha 1? Alpha 1 is sigma 1a plus sigma 2a plus sigma 3a sigma na, and if operate any element from gkf, say sigma, if you operate on alpha 1, sigma alpha 1 would be again alpha 1 as the reason I have explained in earlier theorem. So, similarly, every member of gkf fixes alpha 1, alpha 2, 3, alpha 2, alpha n. Therefore, all these are fixed elements by the group gkf would mean they must belong to the fixed field of gkf. Fixed field of gkf is f. Therefore, all are elements of f. Therefore, this is a polynomial over f. And sigma 1 identity, sigma 1 a is a only. So, a is also a root of the polynomial. So, this is the minimal polynomial. This is a polynomial satisfied by a over f. And what more we will say that the splitting field is a subfield of k, but splitting field contains a, but a generates k, therefore splitting field k itself. Therefore, we found a polynomial over which the k is the splitting field. Hence, one way we have proved. Now, converse, assume K is the splitting field of some polynomial fx belonging to fx. Now we do require a lemma here. What is that? Lemma says if K be the splitting field of fx belong to fx and px be an irreducible factor of fx in fx, if the roots of px are alpha 1, alpha 2, alpha r, then for each I there exists an atomorphism sigma I in GKF such that sigma I alpha 1 is alpha I. How do you prove this? Proof. See, by theorem 2, if you take two roots, say alpha 1 and alpha I, by adjoining alpha 1 to f, you will get extension field of f alpha 1. By adjoining alpha I to f, you will get a extension field f1 dash. And we can have a, by theorem 2, there exists an isomorphism from f alpha 1 to f1 dash I, that is f1 to f1 dash or f alpha 1 to f alpha I. An isomorphism exists mapping alpha 1 onto alpha I and fixing f element wise. Then K can be viewed as a splitting field of fx over f1 as well as over f1 dash. Then there exists by theorem 3, there exists for every I, there exists sigma I in GKF such that sigma I alpha 1 is alpha I, and whose restriction is to f alpha 1 is tau itself, and hence the theorem is true. Therefore, given to two roots alpha 1 and alpha I, you can always find a member of GKF which maps one root onto the other root and whose fixed, whose restriction to f1 is tau itself. Now to prove K is a normal extension of f, it is enough if theta belongs to K and if sigma theta equal to theta for every sigma belong to GKF. So what is a normal extension? It should be finite extension, and next fixed field of GKF is f. Of course, splitting field is a finite extension. Now to prove it is a normal extension, theta belongs to K. If sigma theta equal theta for every sigma belong to GKF, I have to prove that theta is in f. Proof is given by induction on degree of K over f. Assume for any pair K1 F1 of fields K1, degree of K1 over F1 is less than degree of K over F, and K1 is a splitting field of Fx belong to F1x, implies K1 is a normal extension of F1. So whenever you can find two pair of fields K1 F1 whose degree is less than the degree of K over F, and this property holds, and that is Fx is the splitting field, K1 is the splitting field of Fx over F1, then K1 must be normal extension of F1. This is our assumption. Now assume Fx has an irreducible factor. Suppose Fx has no irreducible factor, then F itself is a splitting field which would be, and every field is a normal extension of itself. Trivially the theorem is true. So these ideas would help us in proving main result, and which in turn help us to prove Galois theorem, main theorem. That's what we conclude.
పాఠ్యాంశాలపై మీ సూచనలు, సలహాలు, సందేహాలు మాకు తెలియచేయండి. మీ సూచనలు, సలహాలు, సందేహాలు మాకు తెలియజేయవలసిన చిరునామా: డైరెక్టర్, ఆడియో విజువల్ ప్రొడక్షన్ అండ్ రీసెర్చ్ సెంటర్, డాక్టర్ బిఆర్ అంబేద్కర్ ఓపెన్ యూనివర్సిటీ, ప్రొఫెసర్ జి రామరెడ్డి మార్గ్, రోడ్ నంబర్ 46, జూబ్లీ హిల్స్, హైదరాబాద్ 500033.